I'm Pedro Gonnet, and I'm here with Aidan Chalk, my PhD student. This is this young man down here. All you people looking to hire GPU experts for high-performance computing, hands off. So for the next 3 years, please. We're from Durham University, which is probably not on most of your maps for high-performance computing. This is also an area we've only recently started getting into. I got hired earlier this year. Aidan just started his PhD this year. We don't have that many HPC computing people there. What we do have is a large number of HPC users. We have the Institute of Computational Cosmology, which is notorious for trying to simulate the entire universe. We have a lot of quantum chemists. We have a lot of physicists. So there is a lot of HPC infrastructure there, but very few people active in the development of HPC code. So that's where we fit in. And development is one thing I'm going to talk about today, and more specifically, it's going to be about using asynchronous task-based parallelism directly on GPUs. The NVIDIA people may not be happy with me after this. So I'm going to start in a rather unconventional way just by giving away the punchline just before we start. This will help you know what to focus on and keep you on message throughout the whole talk. So first of all, as the title implies, task-based parallelism on GPUs is possible. But most importantly, it works incredibly well, but only if done correctly. Okay, this is the take-home message. This is a significant break with like the traditional way of programming on GPUs. It sounds kind of weird speaking of traditional with something as new as GPUs. We try to hype this as cutting edge, but there are already some things that can be seen as like the traditional paradigm for GPU programming. What this does, this task-based parallelism, obviously it opens up GPUs for completely new classes of problems which to date were probably not considered as well suited for GPUs. But also, almost as importantly, it provides, task-based parallelism provides a common framework so that we don't have to worry about writing codes for multi-cores in one way and GPUs in another, and maybe the Intel mic in a third way, and parallelism devices in a fourth, and so on. And what I'm trying to do is provide one framework to think about algorithms and actually implement them that is then applicable to a whole set of multi or many core architectures. So first things first, what is task-based parallelism? And as opposed to Intel's presentation earlier today, I don't consider parallel programming to be something that you slap on as the fourth phase out of 5, but it's something that you have to think about from the beginning of when you're designing your code, when you're thinking about your algorithms. It's something that has to flow in from the beginning. And task-based parallelism is just a way of writing your code or just structuring your code such that it is, implicitly parallelizable. And implicitly parallelizable in such a way that avoids most of the problems associated with concurrency and load balancing in an implicit way, so that we don't have to worry about these things explicitly. The way this works is relatively easy. We take an entire computation and break it down into tasks. So the tasks are these round circles here. And for every one of these tasks, for each individual task, we're going to keep track of two things. One is the dependencies, which task it depends on. These are just the arrows here. So that means that before this task executes, both of these tasks here have to have executed. So we get like a directed acyclic graph. On top of that, we're also going to keep track of which tasks this task conflicts with. And now a conflict, what I mean by a conflict is that this task and any other task that it conflicts with, for instance, these two here, are not allowed to execute in parallel. It has to be done one at a time. This can be, or this generally will be, because they access some common resource. They're going to update the same locations in memory, access some same device or whatnot. It's just to tell the system that those two tasks cannot be executed at the same time. They can be done in any order, but not at the same time. Once we have this structure, the way this works in parallel is that every core or every computational task will just pick up one of these tasks, and one of the tasks that has no unresolved dependencies or active conflicts, and just execute it or solve it. So for instance, the first thread can pick up this task here, and that will automatically invalidate this task because, well, it's got a conflict with it. So the next thread comes along and just picks up this task, and that invalidates this other task. When these have done executing, I just take them out of the task tree, and then the threads just keep on picking up the next tasks, and so on and so forth. So it's a very, very simple paradigm. Now, the reason why we do it, why I think this is a good thing, or why a number of people think this is a good thing, well, first of all, something that may seem a bit dodgy is that the order in which the tasks are processed is absolutely non-deterministic. Okay, the threads can go and pick up any task that's ready, and so on. But in this way, it also adapts automatically to load imbalances. So if one of these tasks turns out to be heavier than we thought it would be, or one of the CPUs gets blocked on input-output or whatever, the others just keep on going with the work. It's automatic load balancing. Another very important aspect is that if the dependencies and conflicts are specified correctly, at the level of the individual tasks, so if you imagine the tasks as just like being kernels that are executed, we don't have to worry about any kind of conflicting memory accesses or any form of concurrency problems, because that's already handled by the structure of the tasks. If I've specified the the conflicts correctly, it means I can read and write to memory as I want without worrying about somebody writing in between. Okay? Right, so I don't have to worry about a number of things. This is great because it means that I don't have to do any explicit locking, synchronization, or atomic operations, which all three of these are usually very expensive in a parallel setting, and they don't scale very well. One other thing we can do is when we're specifying these tasks, one thing to keep an eye on is that you can get a program and cut it up into tasks in a billion different ways, but if we look for ways to make these tasks such that every task will only access a very localized portion of memory and do a lot of computation on a restricted amount of data, what we're going to get is some kind of implicit cache reuse. So if you think of GPUs that have shared memory, or the parallel chips that were presented, that'll have a local scratch pad, you only load the memory you need from the main memory, you work on it for your task, and then when you're done, you put it back. And since nobody else is going to be touching that memory anyway, you can do this. So that kind of comes for free. We get good cache reuse just implicitly from the model. All in all, this is just a very dynamic and fine-grained way to do parallelism, and because it's so fine-grained and because it's so dynamic, it has a good potential to scale over a large number of cores. This is something to keep in mind because, as many people have said today, that we're not getting faster cores, but we're getting more and more cores. So Moore's law is now applying to the number of cores. So if we can deal with 16 cores on a computer today, that's all good. Next year it's going to be 32, and the year after that it's going to be 64. So we have to be able to scale with this. So we have to have a model that scales with us. Now, all this is, of course, nothing new. People have been doing this since the 80s, or if anybody can remember anything from back behind the 80s, maybe even there. And there are many libraries that will do task-based parallelism for multi-cores, and even some used for heterogeneous systems. The best-known libraries are Silk, Quark. Well, Silk is now part of Intel's threaded building blocks. Quark was developed for linear algebra. StarPu and SMP Superscalar are computing projects that don't have any real HPC applications yet. They all do this, however, with one significant difference. They do not do conflicts. They only do dependencies. So we're adding conflicts to the mix. We'll see later on why. So that's task-based parallelism. Now, a few words on GPUs. We're all experts on GPUs, so I won't go into too much detail here. I'm going to talk about what I mean by a traditional approach. And this is usually people trying to parallelize their code by unraveling the outermost loop. And this is a way most people are told to think about GPUs because it's the easiest way to imagine how they work. So we imagine that we have an infinite number of threads, and if we have a loop that just adds two vectors and stores them into a third vector that uses n vector elements, we call a kernel that'll just do one iteration of this loop, but we call this kernel n times. And so TID here is just going to be the ID of the thread in which we're in at the moment. And all this is done just in one step with n threads in parallel. So we're given a paradigm in which the GPU is just some massive vector machine which will do everything at once. This is really good for problems that can be formulated as a single loop or as a set of independent loops. This gets a bit more complicated if we start having data dependencies within a loop. Okay, then things aren't as straightforward. If we have these dependencies, things get even more complicated for very large n, because then we have to start splitting things into blocks that are executed independently, and we have to start synchronizing in between them. And things become a complete mess when within this loop, in a data-dependent way, we have several paths of execution, if-then-else statements, in other words, which will cause the threads to diverge, and we're going to lose a lot of performance because of that. So this traditional approach has its limits, and if your problem that you're trying to compute falls in any of these categories, it's not that straightforward. So before going any further, it's worthwhile considering how this actually maps to the hardware on NVIDIA GPUs. Okay, these GPUs have a concept of a streaming multiprocessor, which will actually contain the individual cores. So the whole GPU is actually a set of SMs that have these cores on them. And every block of threads will reside on a single multiprocessor, and that's where its shared memory is also going to be stored. So every block is, for its entire life, it's tied to a single multiprocessor. The multiprocessor will execute the threads in each block in warps of 32 threads each. That should also be nothing new to everybody here. And it's actually only within these warps of 32 threads each that everything is executed in lockstep parallelism. And different warps, even if they're within the same block, we have no guarantee that they will execute in order. It's just that whatever warp is ready to run, it will be run. And then, and so if we need synchronization, we have to do this explicitly. So in summary, what we have is we have a programming model that gives us the illusion that we have an infinite number of threads, just a very, very large number of threads, and things happen in some form of parallelism. But actually what we get is only a finite number of a lockstep parallelism that only works on a finite number of threads at a time. And that finite number is set to 32. So how are we going to take advantage of this? Well, we're going to do 32 threaded multi-cores. So remember that the individual blocks execute independently of each other. So if we make several blocks with 32 threads each only, we can treat each block as an individual core in a multi-core system. And what we're going to have now is that every core is going to have just 32 threads within it, but now executing in strict lockstep. And so, of course, since these 32 threads fit into a single warp, we can guarantee that they will be synchronous without having to do this explicitly. And we can use these atomic compare and swap or atomic add operations provided by CUDA to create some thread-safe primitives and other data structures that we can use to manage tasks. All right? So, by using this, we can open up the GPUs to the task-based parallelism. And the way we do this is to rewrite our kernels in a very simple way. The kernel goes into a loop where, while there are some threads, the first thread in a block will get a task, will pick up a task from some mythical abstract task queue, and then execute that task with all 32 threads in that block. When it's done, it'll go get the next one, and the next one, and the next one, until there are no more tasks left. Okay, very, very straightforward. This is data-driven, asynchronous, because we have several blocks in the system doing this. And it's really a significant departure from what NVIDIA tells you to do. And it's very, in the programming manual, they strongly discourage this. And in the good coding practices, whatever handbook, there's a whole section dedicated to not doing this. But it works quite well. So, yeah. This is a good thing about being an academic. You can do these things and nobody really cares. The main difficulty in all this, though, is something I've just kind of glossed over here, is really getting the next task in the queue. This has to be done as efficiently as possible. So to do this, we're going to use something called lock-free queues. Conceptually, it's, well, I'll get into that. What we have to do, this is the only part of the code on the GPU that actually has to worry about other blocks being there working concurrently. Usually when you have this kind of thread, this kind of task queue, you protect it by a mutex. That's a mutually exclusive barrier, so that only one thread at a time, or in our case, one block at a time, can access this queue. This, however, will become a bottleneck for either large numbers of threads and blocks. So if we have a lot of threads, a lot of blocks accessing the same queue, they're going to get stuck. But also for lightweight tasks. Remember, if we're doing something which normally on the CPU or maybe compute-intensive tasks, now we're doing every task with 32 threads at a time. So ideally, they're going to be 32 times faster, and that means that the tasks get lighter, so it's going to spend more time, relatively speaking, on the queue. So we have to make this queue as quick as possible. And for this, we use lock-free, or sometimes called non-blocking task queues. And the way we're going to build these is simply to make two arrays, data and recycled data. And this is just going to be arrays of integer which hold the IDs of the tasks. So the tasks are numbered, and these are just going to hold these integers. And what I'm going to do is I have, so when I pick up a task, I'm going to pick it up at this first index here, and then check if the task is ready. And it's ready means it has no active conflicts, and it has no pending dependencies. So it means I am allowed to execute that task. If it is ready, I store it into the recycling data at the position recycling last. And if not, if I can't execute it, I just put it back at the end of the queue. So I'm constantly picking out a task, checking if I can do it, and if not, sticking it until the end, until I have one that I can execute, and I'll put that in the recycling queue. All right. When I'm done executing all the tasks here, they're all going to be here at the bottom. And so in the next iteration, so if I'm doing some iterative process, I just swap these two queues around and start over. And now, so I still have all my tasks now in a compact array. Since all operations on this queue are going to be done concurrently, we're going to have several people getting tasks or several blocks getting tasks at the same time. We have to add some extra machinery to make this as thread safe as possible. So the first thing we do, so this is now just the code in CUDA to pick up one task from, this is actual code. This will actually compile and stuff. So when we pick up a task, the first thing we're going to do is check if the queue is empty. I am not going to check the indices first and last. I'm just going to check if I had the actual count stored into the recycling array. This is the criteria I'm going to use for everything done. So what I'm going to do first is just pick up the first entry in the queue, and take this modulo the size of the buffer. Obviously, in the picture it was like an infinite thing. It's not infinite. It's just we just wrap around. That works actually quite nicely. Once I have that index, I actually take a little time to wait to see if there's actually data at that position, because I could have a lot of people that moved from your perspective, move first until it overlaps with last. And by convention, these entries are going to be -1 if there is no task there. So I wait for some other thread to either drop a task back in there or for the queue to be empty. And then once I've passed that stage, I mark off the task that I got with -1. I clear that entry in the queue and return. So here I've only just picked one task ID out of the queue. I haven't put it back or executed or anything. So what we do is we wrap this into another loop, which what it does is it picks off tasks on the queue, and while it has while it actually gets tasks, while the queue is not empty, it checks if the task is ready. And these are just really fast operations. Check if it has dependencies, check if the conflicts are okay, lock any resources that it has to lock. So if the task is ready, it breaks, it leaves this loop. Otherwise, it just puts the task back. And I'm not showing this little bit of code because it's just like one line. It's an atomic instruction that puts it at the last pointer. If we exit this loop with a valid task, I always have to check if I actually did get something. I can do two things. I can either put it back in the recycled data, so I just atomically update this index and dump the task in there, or I have a flag that says, actually, I want to steal that task from that queue. I don't want to put it back in that queue. I want to put it somewhere else. So here, I just decrease the count of that queue. It has one task less. And remember, these are the two indices that I was using to comparing these two to see if the queue was empty. All right, and then when I'm done, I return the task ID. And that's all we need. This is those 20 lines of code are all the machinery we need to efficiently and in a thread-safe way pick tasks off of a queue, to execute them such that their dependencies and conflicts are resolved. I didn't show the actual dependencies and conflicts because that depends how you implement them. So a few notes on this. Getting a task is only a few atomic operations. We're not doing anything massive here. The queue can only ever block when it's almost empty, and that's when the first pointer passes the last pointer, but that's only going to happen just before it dries up. A very important aspect here, the queue is also self-organizing. So I'm dumping things back into this recycled list in the same order, same order in which the tasks were executed in the previous iteration. So if that was a good ordering, well, that's the exact ordering that the threads are going to find the next time they run through the queue. Okay? So basically, I can initialize these queues in a random order, and everything will work out fine after 1 or 2 iterations. Okay, so this isn't all theory. We actually applied this to molecular dynamics simulations. Some basic concepts. People have spoken about MD simulations. We're doing this without dancing. We're just moving atoms around. So basically what we have are short-range interactions between particles. The way we do this is, I'll take a few steps back, is we discretize our grid according to the maximum interaction length. And so we have cells of particles, and every particle interacts only with the particles in its neighboring cells and with the particles in the same cell. And so this gives us a very natural decomposition into our tasks. Our tasks are just a pair of adjacent cells or a cell with itself. And, well, if cells overlap, then we risk updating the forces on this particle from 2 places at the same time. So this is going to be a conflict when 2 cells overlap. And so basically, if we have different tasks doing non-overlapping cells, we can do as many of them as we can fit on this grid in parallel, and nothing bad happens. So to test this, we implemented it in 4 variants. One of them is just that, again, going back to kind of a traditional way of doing things. We still have this concept of tasks, but now no task synchronization, no conflicts, no dependencies. And what we're going to do is we're just going to compute the interaction and store the forces, but we're going to store them with atomic instructions. So we use atomic add to store these forces. Another variant, another traditional way of doing this is blocking. So when we've computed the interaction on a number of particles, usually we do this in chunks of 4 particles at a time to exploit instruction level parallelism. I'm going to block off a cell with a mutex, write the particle forces, and then unlock the cell again. Then now comes our task-based stuff, a single queue for all the blocks on a GPU. And the force, the actual interactions, the tasks themselves use no atomic instructions. And then using multiple queues. So I'm going to make 1 queue per multiprocessor and use work stealing. So if the queue is empty, if a block goes to its queue and its queue is empty, but there are other full queues around, it'll pick a queue at random and steal a task from it and put it back in its own queue. So to load balance between the multiprocessors. This is all part of open source software, blah, blah, blah. We tested this on a medium-sized benchmark. It's a protein in water. It's a 9 by 9 by 6 grid, which gives us a total of 6,800 tasks. So for the results, I'm going to show scaling. Usually people with GPUs, they do not show scaling within a single GPU. So what I'm doing is I'm constantly increasing the number of blocks and showing its parallel efficiency. This is strong scaling. What we can immediately see is at the beginning, the scaling is absolutely awesome until about 12 blocks. I'm doing this on a GPU that has 15 multiprocessors. What's happening here is that every block is getting its own multiprocessor, and at some point they start overlapping multiprocessors, and so we actually start losing performance because several blocks are sharing the same cores. And anyway, why I'm interested in scaling is because, well, we know things are not getting faster, they're getting more parallel. So GPUs will either have more blocks per multiprocessor, so this curve is just going to keep on going, well, this direction, or they can increase the number of multiprocessors, so we're going to get more of this really good scaling here and then only drop off later there. Okay, but this is something people don't really like to talk about. What if GPUs get twice as large? All values here are relative to the multiple queues. Multiple queues and single queues do about just as well. The blocking starts off worse, but then almost breaks even. And what's funny is that the atomic operations are really, really good at the beginning, and then actually, well, as of 40 or 50 blocks, they decay rapidly. This has to do with when you do an atomic add, it's not actually adding things on the GPU cores, but it's actually the memory managing thingy that does the addition for you. So it's a bit of a weird hardware thing that we only realized today. If we look at the cost for the single queue, where is it actually spending time? Well, we can see, so this is the cost of computing pairs, 2 cells beside each other. This is the cost of computing all particles with each other in 1 cell. This accesses a lot less memory, so it grows a lot slower than this. And this is the cost of getting a task. And at the end, at 120 blocks, recall that we're distributing 6,800 tasks on 120 blocks, which means about 50 tasks per block. We're only using 10% of the compute time is overhead for this scaling. What's notable here, the reason why this grows is also not really the overheads, but because we have task starvation, because it's only 50 tasks per block. At some point, there's just no more tasks there to do, so they go crazy. We can fix this by using smaller cells and then doing more cell pairs. What's also important to know here, so we have a very strong increase because the cores do something like hyperthreading. It's several blocks using the same core. And this increase here is stronger than this increase here. So actually, the cost of just loading more blocks onto an SM is larger than the cost of doing the scheduling. So a few notes to these results. This is a very important piece for me because everybody's been talking about the ratio of just flops in general, flops per watt. I'm interested in flops per dollar. I'm originally from a third world country, so these things are important to us. This code, as it's shown here for this example, is 2 times faster than a 16-core cluster node. It's AMD Opteron 8380 running at 2.5 gigahertz. It's 2 times faster, you can say, but it's also 10 times cheaper. So that's a factor of 20 in bang per buck that you're getting there. I don't know how many watts, but this is cheap high-performance computing for the masses. In the previous example, the blocking was slightly faster at high number of blocks, but only because we could structure our core to do 4 updates, 4 interactions in one, and that's not always going to be possible in every type of computation. This is also a biggie. There's no major difference between the code for the CPUs and for the GPUs. So in this MD core package, both things look the same. It's the same task decomposition, and the algorithms for computing the interactions are almost identical. Just in one of them, I'm assuming that I have 32 threads, and in the other, I assume I have 1. It's basically 2 for loops that just loop over both the particles. And also, this is not just some academic pipe dream. These numbers are competitive with production-grade molecular dynamics simulations for GPUs. We're not as fast as the fastest one, but we're faster than the most popular one. So I can live with that. So conclusions and some outlook. So the task-based formulation I presented here is completely general and can be applied to several problems. One of them, for instance, is numerical linear algebra. So I have a student, Sam Townsend, third-year student in computer science, who's using this to implement tiled linear algebra for QR, LU, and Cholesky decompositions directly on the GPU. So you send it off to the GPU, and the GPU does all their task-based magic. And we're also working with the computational cosmology people to do smooth particle hydrodynamics. We're not talking about the SPH variant, which is fixed radius, but the one with variable radiuses and several orders of magnitude between particle sizes, and that does not traditionally map well to GPUs. The big issue here is task selection. We're looking for more efficient queue structures and algorithms. We're looking for queue distribution strategies and also task clustering strategies. And especially, we're interested very much in seeing how this will work on other many-core architectures, such as the Mike and on the Epiphany chip from Adaptiva. So again, the take-home message is, I hope I've made all of these clear, and thank you very much for your attention.
So if our next speaker would like to come up and set up while we take 1 or 2 questions. One here. Going to be any on the other side?
Hi, Jonathan Hogg, STFC. So we've been implementing linear algebra algorithms using tasks for a while. One major problem that we have is a lot of our users want to get the same answer every time they run the code. but because it's not a deterministic order you're adding things up in, you get slightly different answers due to floating point.
Yes.
Have you got any solutions that you can offer us to that?
Actually, this is one of the questions that people from molecular dynamics had, and the answers always get real. I mean, the differences you're getting in the answers are just different errors. It's not the digits that are correct mathematically, that are within the accuracy of your computation, those will always be the same. But whatever, you're just going to get a different rounding error, but it's still going to be the same accurate result.
Yeah, so you've got an equally valid result, but this has a knock-on effect. So a lot of our codes end up inside of optimization packages. If it's non-linear, then it's not necessarily stable, and you may get different optima found. And if that's then used in, say, finance, they can't actually use that because they need to be able to replicate the answer they got, so they can justify to the regulator, this is why we sold this share then.
Right. Then you need better optimization algorithms that don't react that sensibly to noise. That's yeah.
It's a problem we've heard of a few times, actually.
But you can't rely on noise being non-noisy. It's it's just as I was a numerical analyst for 3 years of my career. It's that doesn't exist. Any other questions?
Any more? One at the front.
Hi, Bill Langdon, UCL. I wondered if you'd considered having more than 32 threads per task.
No, because then if we have more than 32 threads, we cannot guarantee that they are strictly in lockstep. That does matter, because when we're reading and writing to memory, we want to make sure that we're not stepping on other blocks' feet. We don't want to start stepping on our own feet. In this case, it does matter. Without going into too much detail, it is a huge difference if I can assume that for every instruction, it's being done in strict lockstep. Because then I can interleave reads and writes to the same addresses, and nothing bad will happen. Promised.
Two more. I'll come along the front.
Hi, when you run on, you say that you use the same code to run on the CPU, but you just assume there's one thread. That sounds like you're not taking advantage of the vector SIMD units in the CPU. Should you not really be running with a small number of threads in the CPU which get mapped to SIMD instructions?
So on the CPU, what I actually do is when I'm accumulating interactions, the interactions are written as piecewise polynomials, so there are no if-then-else statements to actually compute the different interactions. And so I just stack up 4 or 8 interactions and then do those in SIMD. I don't do that on the GPU, obviously, because there's no SIMD on the GPU. I just do 32 at a time that come out of the loop. So I think I'll hand over to...
I know we had a few more, but just looking at the time, we better press on. Grab these guys afterwards if you need to.
We won't be going anywhere quick because our flight leaves only like in 3 hours.
All right, okay, so thank you again, Pedro. Cheers.